Welcome to this new lecture of Robotics 2. This will be our last lecture of this academic year, and it will be devoted to the topic of human-robot coexistence and collaboration. This is a very important and hot topic, both in industry and in service, because human and robots will get closer and closer as they collaborate in executing complex tasks. I will start with a conventional point of view. So the traditional robotics was the one in which robots were replacing human and typically on the factory floor. Now we are talking since a few years about a new different type of robotics, namely human-friendly robotics, where robot will collaborate with humans, both on the factory floors, and the name that they are given would be co-workers, so working together cooperatively with the humans, or also personal robot in service application at home, in hospital, and so on. This would mean that there is a proximity that is being planned between humans and robots, physically and cognitive, and we have to consider a number of things in order that this may happen in a safe and consistent way. The results that I'm presenting are most research-oriented, developed over a number of years through European projects, first France, as I already mentioned, and mainly the Saphari project that we coordinated as Sapienza University of Rome between 2011 and 2015. And as you can see from the partner and the main topics, we try to cover all aspects which are important in the interaction, in particular the physical interaction between humans and robots, covering the aspect, the paramount important aspect of safety, but also an intuitive way of communicating with robots. Revisiting most parts of robotics, starting from the mechanical part, the mechatronic designs, the inclusion of compliance, lightweight design of robot, to the generation of plans which take into account or put into the center the human in the present and is present in the workspace. We revisited also the idea of reactive control, so reacting to sensor information in a very dynamic and changing and unpredictable environment. So we need sensor for doing real-time perception. We have to learn from human and interpret what human are doing in much the same way as human should understand what the robot is planned to do. And last but not least, controlling the interaction, the physical interaction. In this lecture, I will cover essentially these two topics. So real-time perception, namely the way of using sensor for monitoring the workspace in which the robot operates, and understanding relative distance with other agents, in particular human. And then interaction control, in particular physical interaction control, so the possibility of controlling exchanging forces in a safe way between the robot and the human. So in our plan of lecture, we have seen a first basic block of this hierarchy of behavior. And in all cases, we formulate control problems which are strictly related to safety. So we have seen that we were able, without the use of external sensing, so using only proprioceptive devices which are on board of the robot, to detect and even isolate collision. So unintended contacts between the human and the robots. And also we have seen a number of reactions which were mainly intended to abandon the area of contact, possibly continue to keep the robotic task in operation if this is safe enough. Now, the next step, or if you wish, the previous step, would be to avoid this type of collision or unintended contact, which would mean that we need now sensor for monitoring the workspace continuously and let the robot react to vicinity, not just contact, which is the last, the last moment of this interaction. So avoiding collision while doing the task, or abandoning the task for a while and then resuming the task as soon as the danger is passed. The danger is considered to be the human too close to the robot motion. Indeed, in this case, there will be no exchange of forces, no contact at all. If something goes wrong and we have a collision, then the detection level will intervene. But of course, there are other situations in which we would like to enter in contact with the robot because we would like to collaborate physically. For instance, carrying together a load. So we have to estimate what are the forces at the contact. These are intentional forces which are exchanged, and we may wish to use a force torque sensor or even proceed like in the first problem that we have seen without the use of any other sensor devoted to this purpose. Of course, we may use whatever we have developed for monitoring the workspace, so proximity sensing, together with signal that we can generate in response to a collision, so to detect a collision, we may combine these two, and in fact, we will combine these two types of information in order to achieve this goal of physical human-robot collaboration. Now, a few years ago, we set up a control architecture that tried to capture all the robot behavior which are relevant for this problem in a consistent way. So the solution to the problem goes indeed through a design, an integrated design, and a combined use of several components from hardware to software. So soft mechanics, which mean compliant, lightweight arm, actuation, which may also be compliant, and variable according to the type of task that the robot should do together with the human. And of course, extensive use of sensing, proprioceptive and exteroceptive, communication between robot and human or between robot and robot, and indeed, everything is being orchestrated by control algorithms. So we decided that 3 levels were satisfactory to address the problem. The inner level, or the lower level, if you wish, is safety. The second, we call it coexistence. And finally, collaboration. We will see now in detail each of these levels, what is devoted to and how they interact. So first of all, the always active level is the safety level. In fact, this is the most important feature that a robot should possess in order to be to work together with humans. The classical solution that has been adopted in the factory floor was using cages or protecting the human from any movement and operation of the robot. So when the robot is in action, the human is not there. When the human is there for programming or maintaining the robotic system is switched off. So these, of course, are not appropriate solution for physical human-robot interaction in the sense that we foresee to have. So safety should be guaranteed in different way. And one way, for instance, is to use a collision detection method, which are reliable and practical and on board, like we have seen. Together with this, indeed, the design of lightweight arms, compliance at robot joints, and probably also some software parallel architecture that guarantee continuous operation even in the presence of failure. All this goes into the domain of safety. You should think that because of the relevance of safety on the workplace, there has been a number of standards that have been devoted to safety, and in particular to safety of robots. The most famous one is the ISO 10218, which was developed in 2011 and then updated later on. We'll say more about this standard in a few moments. So this is the ground layer of our architecture. So safety should be always on. Now, indeed, the next level is coexistence. So for us, coexistence means the capability of the robot to share its own workspace with other robots, with other entities, but most relevant with humans. So for instance, in the two sequence of snapshot that you see in this slide, you may have a robot which is doing his original task, so moving around, doing some pick and place and operation, and all of a sudden the human intervenes because it does something in parallel with the robot. So coexistence means that there is no need of exchange of forces. So no need of physical contact. So the robot should continue to do its operation while the human is present. Of course, abandon the operation if the human enters or comes too close to the robot, and then recover operation. Now, this is coexistence. Indeed, if something goes wrong, because the human may do a very fast motion, which the robot or the robot sensing is not able to capture, so there could be a collision or a contact. So the safety layer comes into place, and this is why we call the interaction between the coexistence level and the safety level safe coexistence. So safe is always there, and we will see some nice video demonstrating what we do mean by safety and coexistence, and even more with the third layer of collaboration. So this is the most complex task, collaboration. So it's at the top of this hierarchy. And of course, collaborating should be, again, consistent with the other behavior. So collaborating means having the robot and the human do typically complex tasks with interaction and coordination. Now, there could be contactless collaboration and physical collaboration. These two modalities are not mutually exclusive. By contactless, we mean, for instance, communication by gesture or voice command, or both, or even visual coordination. So the robot is following the human as the human is doing something, or the human is showing something to the robot, and the robot is replicating this type of behavior. There is no contact involved, but there is a coordinated motion, so we call this also collaboration. But in fact, we were more interested in particular in the Saphari project, in the physical collaboration, which, as I said, involves intentional contact. So we should not avoid contact. We should recognize that human and robot should enter into contact and exchange forces. And of course, this exchange of forces should be controlled. By the way, there is no a priori specification of where this contact may occur, not necessarily at the level of the end effector of the robot, in much the same way as this interaction may not be done with the human hands, which are the end effector of the human. So the whole body, for the robot and for the human, should be considered in this case. Now, collaboration should proceed, and it's really the most sophisticated aspect of this interaction. But of course, you should still coexist with the robot for what else you are not doing in a collaborative way. For instance, if you're holding an object with your right hand and the robot is in contact with your right hand holding this object, of course, with the rest of your body, you should not get in contact with the robot. So you should still coexist while doing a collaboration. And if something goes wrong, the safety layer is always present to react and stop or escape a dangerous situation. So in this sense, this is a general hierarchy that we developed and we tested, in fact, in all its components over the last few years. And by the way, on different systems. Indeed, collaborative operations are also normed by standard. In particular, the standard ISO 10 to 2018 1, which concerned the single robot, and 2, which concerns the robotic system as a whole, and lately refined by a technical specification, the notation with the column and the year. The year stands for the year of publication of the standard or of the technical specification, TS, which is not yet a standard. So the last one is of 2016, is the 15066. So in this context, there have been some effort in specifying what should be done, what can be done, what cannot be done, and classify the level of interaction, which are generically defined as collaborative operation, even if there's no physical collaboration in the sense that we have just mentioned. So the simplest level, the level 1, is the so-called safety-rated monitor stop. So the fact that the human is entering in the vicinity of the robot, and the robot, through its external sensors, camera, lasers, proximity sensor, time of flight, whatever you name it, recognize this proximity and stops. Okay. Now it doesn't stop in a catastrophic way, because this type of stop is already, let's say, programmed so that the robot may resume its operation from that moment. It's not an alarm stop where you push the red button and then you have to restart the system. The next level is the so-called hand guidance. Now, this is an old way of programming the robot. So having the actuators just sustain the weight of the robot and then moving around the end effector with some special handle and letting the robot go to different positions, which are then recorded and then repeated in an online operation. So in hand guiding, of course, you are in contact with the robot. The robot is, the supply is on, so the motors are on, at least for sustaining the own weight of the robot itself. So this is a kind of a critical situation, but in fact, the robot will not move unless you're moving it on purpose from the end effector. The third level is a refinement of the first one, which means that before stopping, in fact, you can define different areas, different distance between the human and the robot. So in the green area, the farthest away, so the robot, the farthest away from the robot, the human is allowed to enter, the robot continues to operate, probably sets a flag on, so internally check more often the external sensor because of this potential vicinity of the human. When the human enters in a second region, the yellow one here, typically the speed is going to be reduced. So whatever the robot was doing is now slowing down because, of course, the harm of a potential collision grows with the speed of the robot. Of course, depends also on the type of tool that the robot is mounting. If it's a dangerous tool or not. Even the gripper may be a dangerous tool because it can close around the part of the human body, the hand, or so on. So there should be a speed reduction. And of course, if you get too close, the robot just stop and wait, just like in level 1. And finally, the most interesting part is the level 4, where in fact human and robot are physically collaborating, so they are exchanging forces, and the standard has set some limits to power and force. In the technical specification, there has been a biomechanical study, depending on which part of the human body gets in contact with the robot, setting maximum force or pressure limits depending on the part of the human body, the skull, the arm, the torso, the legs, and so on. So there is, in any case, a limit on the force and on the total power of the robot, which means that if the power is limited, for instance, to 80 watt, this is a number that appears in the standard, then of course, whatever will happen, you cannot transfer more than 80 watts to the human body. So this means that 80 watt are easily surpassed if you have a very massive robot moving even slowly. But if you have a lightweight robots, then you can afford more velocity. And of course, this limitation is in action when you're within the level 4. So if the robot is not moving, but still using power, there is a limitation to that if you want to satisfy and certify these standards, which means that you can certify and sell your system to a generic user, which is very important. Indeed, at the level of research, we are not yet concerned with that, but if you want to move a product or a result from the research lab to industry, then we have to comply also with this standard. Now, how this relates with our three-level architecture, control architecture. So again, here are the 4 levels of the ISO standard. On the left side, you see also a pyramid which classify the type of standard. Of course, there are standards which concern generic machine, mechanical machine, electrical machine, and then on top of that, there are specific standards, for instance, for robots. And here you have a number of relevant standards in industry and in production. So if you look more carefully, and here on the right-hand side, we have our 3 layers, and I single out some specific tasks that are assigned to each level. To the safety, we mentioned collision detection and reaction. To the coexistence, sharing the workspace, monitoring the workspace with extra sensors with the purpose of collision avoidance, and of course collaboration, coordinated motion and action with or without contact. In the table on top of this, in the brown table, you see that for each level, there are some specification in the ISO standard about speed, about separation distance, about maximum torques, about controls that should be available to the operator, and how to reduce, so a risk analysis and assessment and a mitigation of the possible risk by special action. And you see that I've put some ellipses that relates the various level to our architecture. Indeed, safety goes across all these 4 levels of collaboration. Our collaboration, so physical or with coordination, is related to the hand guidance, so level 2, or to the power and force limitation, which is level 4, while coexistence indeed involves level 1 and 3, so stopping or slowing down and possibly stopping, but still monitoring relative distance between the human and the robot. So we fit into this type of standards, although we developed our control methodologies rather independently from that. Okay, so we have seen dealing with collision detection and isolation that we have defined a collision event pipeline. So if we, for instance, consider the problem of handling collision, we have this type of continuous circle going on. So we plan motion to prevent collisions, but indeed, because of the highly dynamic and unpredictable environment, because of the presence of humans, this plan may even fail. So we control the robot, the motion of the robot in real time to avoid contact, so to escape from possible collisions. If this is not achieved for a number of reasons, then we should detect that we have had a collision, isolate the link that collided, and possibly also distinguish if this is a severe collision or not. And maybe if it's a soft collision, it could be also an intentional contact that the human is searching. So by using the contact in order to provide some command, for instance, the intention to collaborate. In any case, once we have classified the type of contact or collision, then we react or replan motion. For instance, if the robot switch mode and is ready to collaborate from now on. Okay, so this is a continuous circle. Of course, you can restart, plan to prevent, and so on and so on. Now, we have seen so far the detection, isolation, and reaction. Not much about distinguishing, although we have seen that we can distinguish soft from hard contact in the closed control architecture of the KUKA KR5 by processing, filtering, high filtering and low pass filtering the motor currents. But we will see more on that today. So these are part of the full collision event pipeline that we have already seen with monitor signals that are being generated and information coming from the context. Now, I'm showing this slide again because I would like to put it in perspective with respect to the 3 layers of our control architecture. So coexistence occurs in the pre-collision phase, in fact. So the purpose of coexistence is, in fact, not to arrive to a collision to be detected. Okay. Indeed, safety in this case is really fast recognition, detection, and reaction to this collision, while collaboration may start at the level of reaction once we have identified the type of contact, classified if it's intentional, light, and in fact, we can interpret it as the intention to collaborate, then our reaction will not be just stopping, slowing down, or escaping the area of contact, but switch or be ready from the point of view of the robot to start to collaborate. So this fits, puts the collision event pipeline into the context of our control architecture. Now, just to recall what was the safety part that we developed from the point of view of software, so collision detection and reaction based on residuals, so monitoring the total energy or the generalized momentum. And this was mainly work done with the previous project, the Friends project, also financed by the European Community. So you can see that there are possible reactions, the reflex reaction, generating torques which amplify the result from the collision so that the robot flies away from the area. The admittance mode was commanding the motion in the joint space proportionally to the amplitude of the residual, and of course the residual goes to zero as soon as the contact is lost. So you see that the reaction in admittance mode is more stiff in a sense, as opposed to the smooth behavior with the reflex torque. Okay, so this is done in a sense. So this belongs to the layer of safety. So from now on, we will move to the second layer and then the third layer of collaboration. And my presentation will develop the two layers one after the other. So at this point, I would like to show you a couple of videos that tell us the story. So the early days, this is a video, informational video developed by the National Institute of Occupational Safety and Health of USA in 1989. And then one video coming about 23 years later. It's a commercial video by ABB. It's just an extract from a longer video, which presents some hardware, the electronic position switch that allows the robot to stop when something goes wrong, and also the software, which is the Safe Move software, which implements some of the idea which were presented also in the safety standard ISO 10280. Now I have to switch to a different modality now, so please comply with me. So the video have also some audio, so I will not say anything during the projection of the videos.
Robots have brought about more productive manufacturing lines and greater quality assurance. Their use has saved people from having to work in hot, toxic, or otherwise dangerous environments. Automated production lines using robots are chalking up an admirable safety record. However, industrial robots have injured people, and injuries may occur more frequently as the number of working robots increases. In at least one case in 1984, a worker was killed. The victim entered the working range of the robot, presumably to clean up scrap metal that had accumulated on the floor. The work cell control systems did not sense his presence, and as a result, the worker was pinned between the back end of the robot and a steel safety pole. His heart stopped. No matter how automated a manufacturing line is, there are sure to be workers around who must be protected. Line operators. Maintenance workers. Programmers. Managers and visitors. Robots have weak sensing capabilities, so they can't be relied upon to always react in a safe way when these workers approach. Safeguarding robots is more complex than safeguarding other types of machines. Their range of movement is much greater than other machines. Machine guards around belts, other moving parts, and points of operation are small in comparison to robotic work cells that often encompass several cubic yards on the plant floor. Robot guarding has to be flexible, too, to adapt to the variety of tasks a single robot may perform.
So, as you have heard, there was a big concern about potential of injuries, of incidents that could happen on the factory floor. And one reason for that was that the robots had low sensing capabilities. And this, of course, has dramatically changed in between. But just to understand where we were coming from. Now, the next video, as I said, is 23 years later. and we'll show some commercial products by ABB Robotics.
With the function EPS, electronic position switch, the conventional limit switches used to restrict the working range of the robot are fully replaced by a software function. If, for example, due to a programming error, the robot attempts to access a forbidden access zone, it will be switched off by the safety controller. The interaction between a worker and a robot, such as for manually loading a gripper with a workpiece, becomes possible with the Safe Move function. With Safe Move, the safety controller supervises the safe standstill of the robot during the time the worker is within the hazardous zone. Furthermore, Safe Move allows limiting the robot movement to predefined zones in the space in order to enable safe coexistence of human and robot. It also allows restricting the traveling velocity of the robot to a preset value. To enable humans and robots to optimally complement one another while carrying out manufacturing tasks together, it is necessary that the position of the worker is spatially detected in a safe manner at all times. In principle, this can be achieved, for example, through camera systems which constantly monitor the workspace of the robot and the position of the worker and continuously transmit this information to the control system. If robot and human approach one another, the control system can then first reduce the velocity of the robot until it finally switches the robot off completely in case the distance between worker and robot falls below a preset distance. This method allows safe implementation of new semi-automated manufacturing strategies that were not possible up to now.
Okay, so as you have heard, about 8 years ago, again, still in the manufacturing area of ABB, they were starting developing this safe move software. Now things have progressed in between, but you may have recognized that the speaker mentioned a couple of aspects. So slowing down motion, stopping the motion. Everything is controlled by a monitor of the workspace. In particular, they were using laser scanner in this context. You have seen a laser scanner in front of the window, which was open when the human brought in a part and wrote the logo of ABB, and on a table which was supported by the robot. And in all other operations, there is always a camera or laser or proximity sensor monitoring distances. So things have developed. And in fact, in 2016, ABB has issued the Safe Move 2, which is certified. So this is a demo on a exposition in Singapore in November 2016, which is simpler than the one that we've seen before. There is no audio, so I can run it right now. So this is, I would say, today's operation. So this is an ABB, is white, it's not orange. And this, just for the matter of representation, shows the area that are being monitored. You see at the base of the robot, there are two laser scanners, the yellow boxes, right and left. So when the human enters the slow area, it reduces its own motion. When it enters the stop area, for instance, for inspecting the end effector content, the robot stops completely. Then restarts because you are in the slow area, and when you're out of this, you're completely off. Okay, so quite about the same time in Saphari and in previously in France, we developed our architecture, And in fact, we have here a summarizing video, which it's a 3-minute video. So again, with audio, I will stay calm for these 3 minutes, which shows our concept. And you will see that our concept, especially for testing distances between the human and the robot, is much more flexible. Okay, so it allows the human to get much closer, still in safety condition, to the robot. There's a difference because we use here a lightweight robot by KUKA, not an industrial one. But apart from that, the operative conditions are quite similar. In the video by ABB, they were using 2 laser scanner. We are using here just one Kinect depth sensor, which is, by the way, a very cheap one. But indeed, our solution has not yet been certified by the institution which are devoted to this. So it cannot be moved directly to a industrial setting without this certification. But this may be done. It's something that we are not particularly interested to do personally, but there are some transfer activity of this type of stuff. So next video is safe physical human robot collaboration, and it dates 2013.
Within the FP7 European project Saphari, we have proposed a framework for physical collaboration between humans and robots that goes beyond conventional solutions for preserving safety. Safety is the most important feature for robots working close to humans. Coexistence is the robot capability of sharing its workspace with other entities. Collaboration occurs when the robot performs a complex task with a direct human interaction and coordination. Safety is guaranteed by a collision avoidance method based on a depth sensor, the Kinects. Points of interest on the robots are projected in the depth image, where robots to obstacle distances are computed in a fast way, taking into account also obstacle occlusions. Collision avoidance is performed in real time. Besides tracking the human pose, also static or moving obstacles are detected, tracked, and avoided. Multiple obstacles are avoided as well. Except for the end effector, all other robot points of interest will treat obstacles as geometric constraints in the Cartesian space. A collaboration phase is started by the user with a simple gesture. Contact points are localized using the depth sensor. This geometric information is collected together with the joint torques resulting from the contact, as obtained by our residual-based estimator. Combining this data allows an estimation of the exchanged forces at the contact point, those used by the human for guiding the robot. The user requests to end the collaboration phase by pushing on the robot and effector. Safe coexistence is guaranteed. Only the designated collaborating hand is allowed to get in contact with the robot and effector. All other entities are still considered as obstacles. Robots and humans for a safe physical collaboration. More results on safe physical collaboration tasks are underway within the Saphari project. Stay tuned.
Okay, so apart from the music, which is horrible but was free, you have seen all the development that we have made, in particular by measuring distances between the robot and the human, and we use a depth space approach, and now I will show you how this works, which allows to get very close to the human, in fact, between the human and the robot, before stopping the robot or moving it away. The second part instead is more devoted to collaboration. This was our first attempt to do collaboration only at the end effector level. And you have seen what I called consistency between collaboration and coexistence. At some point, Fabrizio Flacco was the person in the video, is holding the end effector and moving it against his other arm. So because collaboration was in action, the robot was following at the end effector level the human hand. But since coexistence is more important for the other part, then trying to bring the robot against his other arm made the robot very stiff, so that Fabrizio could not really bring it in contact. So at this stage, you have a safe collaboration or a coexisting collaboration, because the two levels have interacted in this way. Okay, so let's move on and consider the problem of collision avoidance. Of course, we need to have exteroceptive sensor monitoring the workspace, and there could be a large variety of sensors. In fact, for instance, laser scanner that were used mostly for navigation in robotics. Now the main target is to provide information on human to robot distances in safety cells. You can have stereo vision, you can have single camera, multiple camera, Kinect, depth sensors, presence sensor, or structured light. So you can combine a variety of sensors, also of different cost indeed. And one main problem is where to put the sensor around the cell. So you should try to minimize areas which are not covered by any sensor. Indeed, you don't want to use a large number of them, so you have an optimization problem, which takes into account also the probability that the human will stay in some area around the robot. For instance, if most of the time the human will be in front of the robot and not on its back, then it is clear that our sensor will be more pointing this area rather than the other. So this type of intuitive idea can be formalized into an optimization problem that decides where to put the sensor. For instance, in the central figure, you see two half circle, and you parameterize the position of a depth and a presence sensor, and then you find the optimal location based on some probability distribution of where the human and the robot will operate the most. So we decided to use the depth information. Depth information are coming from so-called RGBD sensor, so camera, which are equipped also with an extra laser information, which allows to reconstruct also the depth and to associate to each pixel of the image also a depth of the object which are being seen. So here in this typical image in yellow and black, the lighter is the color of a pixel, the closer is the object. So objects which are far away are pretty much dark. Now, once you have collected this image, how to use it in order to understand relative distances between a moving robot and object in the environment, which may be either static or moving like a human. Okay, and there have been over the years a number of approaches working in the configuration space of the robot, which is the typical motion planning space that is being used. You will hear about this more in the course of Autonomous and Mobile Robotics by Professor Oriola, or directly in the Cartesian space, which makes sense, especially if you want to reconstruct the environment. But in fact, we don't want to reconstruct the environment, the 3D environment. We just need to compute distance, very quick, very fast, and very reliable. And this is why we opted to work directly in the depth space, so in the space of the sensor itself. But before moving to the depth space, what it is and how it's being used, let's see what are the other options. So let's start with working the Cartesian space. And again, here we have a video developed at the Technical University of Munich, which describe the use of camera or depth sensors with multiple field of views and reconstruction in the Cartesian space of object. Now you see the human hand being mapped, and associated to this, you will build an object, a geometric object, which will be used for making computation. But indeed, you are reconstructing, in fact, all the objects in the 3D space. And here is how it works. You see on the left the image. So one very important stuff is that the robot is being removed from the picture. Otherwise, it would be considered an obstacle itself, and it would always auto-collide in the sense that it will be closest to its own body, and so there will be a dangerous situation. So this object, this robot, is being removed from the image. All the other objects are being perceived by the sensing devices. Indeed, there will be some gray area. You will cluster obstacle, but at the end, you will like to reconstruct, in fact, 3D object in the Cartesian space. And from there on, you can plan motion or react to motion. And here is a demo with the Kinect overlooking the scene, and you see on the back the reconstruction of the 3D environment of human puppets, I would say. And of course, the robot who's not moving will retract as soon as you get close to it. So this was an approach that was pursued for a while, but then outperformed by other methods. Now, configuration space is the more traditional way. This is a very old video developed at the University of Pisa, and is typically applied only if you have very few degrees of freedom. So here you have a stereo camera. You can see it on the left, overlooking the motion of this soft arm. And this is described visually the operation that are being done in order to construct a representation of the obstacle, a human arm here, and of the robot in the configuration space. So there's a matching of features. And from there, you can build a depth map from the stereo image so that at this point, you have an information about all the objects which are present in the field of view of the camera. Now, indeed, when you move the robot, you know at every time which is its configuration. You have a geometric CAD of the model of the robot, so you can do computation of what part of the configuration space is being covered. And now finally, you construct the so-called C obstacle, so the image of obstacle in the C space. And in the C space, the robot becomes just a point, and you can plan a path which avoids collision. You can see it in red in this 3D view. Of course, this can be visualized if you have 3 degrees of freedom, so 3-dimensional configuration space. For higher dimension, things can be done, but becomes computationally very intensive and not visualizable. And here you see the final results. It's the robot getting around the obstacle. Of course, this is being done in real time, but you have seen the whole process detailed in this video. And finally, the depth space. So we adopted this one because it is very convenient, very fast, and very reliable. So the depth space is a so-called 2.5 dimensional space because it lives on the image plane. So we have each pixel in the image plane is associated to points along a ray which pass through the optical center of the lens. But together with this, there's a third information, which is the depth of the point with respect to the image plane. So along each ray, you can tell that Cartesian point, how it projects into one pixel of the image, and what is its distance from the image plane. So if you have a Cartesian point in a reference frame with some coordinate, then you have to transform it into the coordinate frame of the sensor, which has a z-axis along the axis, focal axis of the camera, and you can give the coordinate of this point in the depth space by associating the 2-point px and py on the image plane with the depth, which is the extra information provided by the depth sensor. So it is, in fact, almost a 3D information, but it's associated to each pixel of the image. And it's a distance in terms of this pixel from the object along each ray coming out of the camera itself. Indeed, here you can see the projection, you can see the actual environment. There's a human, there's a KUKA lightweight robot, and there are rays covering in gray beyond this object, because indeed, beyond what you see from the camera or from the depth sensor, you don't know what there is. So these are gray areas that are potentially full of obstacles if you want to be conservative, or maybe completely free. Now, once you have this depth space, you can start computing distances. Distances between the robot body and whatever is present in the surrounding. Now, in order to make things efficiently, one associates a number of points of interest on the robot. For instance, in the KUKA that you see on the bottom picture, there were 8 points of interest selected along the structure, including the last point at the tip. And around these points, there are area, region, which we monitor for presence of obstacles, which means that with our Kinect, so the depth sensor that we have used, we are looking at the distances of the depth of points which are in the surveillance area for each of these points of interest. And then we can compute the distance in a rather conservative way. So we elaborate these 3 components, one in the depth space. So the first 2 are distances in the XY direction. The third is a depth distance. So the distance of the object with respect, the depth of the object minus the depth of the point of interest. Remember that we know where the point of interest are because we know the kinematics of the robot. We get information from the encoder, so we know at every time where are these points on the robot. On the other hand, so we can associate to them a depth value, or let's say a representation in the depth space. So 3 values px, py, and dp. The obstacle point instead is being detected on the region of interest by the sensor, and again it is represented by OX, OY, so the position on the image plane, and a depth d0. So from there you can compute the distance like an Euclidean distance. The only point of notable point, I would say, is what happens if the depth of the obstacle point is less than the depth of the point of interest. So in the image on the left side of this slide, when the first point is closer, then of course all the things that lie on the line beyond this point are in the gray area. So we don't know if there is something or if this is free. So in order to be conservative, we assume that everything will be full. So if the depth of the obstacle point is smaller than the depth of the point of interest, then in computing the distance, we will replace to the depth of the obstacle point the depth of the point itself, so that we will bring to zero the VZ component, and so the distance will be certainly less than that. If the reverse is true, then we will compute the distance in the regular way. Okay, so with this simple rule, we can immediately have an idea of the closeness of the obstacle point from each point of interest. Now, once we have this type of distance, then we can apply a standard method, which is a repulsive method. So it is based on a version of artificial potential, so that the motion of the robot will be pushed away from the closest obstacle. And in order to do this, once we have a distance vector between a point of interest, so we are considering a single point of interest now and a single object. So we have a distance, dpo, and we will move in the direction of this distance, which is a vector. So we normalize this vector to characterize the distance. So we divide d by the norm of d itself, and we add a scalar to define the intensity by which we will move away the point of interest from this obstacle. And there's a function that modulates this repulsion. Of course, it's maximum when we are very close to zero, and then goes to zero when the distance is far enough. So we can detect that there's a point there, but it's far enough not to let the robot have any repulsive reaction. Now, in order to improve the behavior of this repulsion and to avoid some zigzagging operation or continuous switching between closest obstacle, now, if we consider for each point of interest all obstacles which are near, so which are in the region of interest of this control point, so for each of them, we compute the repulsive vector. Now, the total, the direction that of the resulting motion will be the sum of all repulsive vector. So we are averaging, in fact, the repulsing of each point so that we don't have discontinuities. Because if you have one point being the closest and giving also the direction of repulsion, and while moving another point becomes the closest and gives a different direction, then you will typically switch from one to the other and have a jerky behavior for the robot. If you consider all obstacles at the same time, you have a much smoother behavior. Indeed, the magnitude, however, is given by the nearest obstacle only. So the most dangerous obstacle gives also the magnitude of the repulsion, while the direction is an average of all obstacles. Of course, if there's only one obstacle, then magnitude and orientation are given by this single obstacle point. There are also situations where we need to avoid very fast obstacle getting toward the robot, for instance, a human progressing against the robot itself. So we need some other strategy for avoiding the so-called local minima of artificial potential. And one of these strategies is the pivoting strategy that I'll show you next. But before doing that, there are two videos here that illustrate the behavior of this construction. So the construction of the distance and generation of a repulsive vector and handling of multiple obstacles close to the point of interest in order to see what happens. The first video, here on the left, shows a red point, which is the point of interest, while Fabrizio is bringing its hand closer to it, or multiple hands, and you see the green and blue lines are the single repulsion, and here you see the same story in the depth space, and you can see how you can combine repulsion to get a common one. Now this is obstacles moving around a fixed point of interest. Now this fixed point of interest now is placed outside the robot, but in fact, in general, is one of the point of the robot and moves together with the robot. Now the second video shows instead the point of interest moving, still not on the robot. You see that now it's getting closer to the table, and you see that the repulsion, both the intensity and the direction, and now it's moving around and now getting closer to the robot itself. So feeling points of the robot as being obstacle. So now you're moving in the depth space this point. So you're moving the point in the Cartesian space, but this is the view from the depth space, and the computation, as I said, are made all in the depth space. So we are representing it also in the depth space. Now it's getting down to the table. It will feel some surface first, move close to an obstacle, placed on the table, and this is the view on the table, and so on. So you think this is just a qualitative, of course, you don't have numbers here, but just to say, just to support the idea that this mixed combination is in fact very effective. So there are situations where just repulsion is not enough, especially if the obstacle, now represented by a disk, a red disk, moves faster and against one of the point of interest, one of the control points of the robot. So what happens? If you just go away in the direction of the minimum distance, the following situation will occur. And the obstacle, which is faster, will hit the point of interest. So the idea is very simple. Instead of just going in the repulsive direction, you look at the velocity, the relative velocity of the obstacle, and then you try to escape by imposing a rotation, a pivoting around the variation of velocity. So you avoid, in fact, the obstacle in this way. Of course, you can combine and you can generate even other method. Here below, you see the behavior with the modification of the variation of the repulsive vector, so to circumvent, in the sense, pivot around the obstacle coming against the robot point. And here, if you're interested, I also recorded a very short code doing this pivoting operation. I will leave this for your reading afterwards. Now, we have considered one control point, one point of interest at the time, but in fact, we will handle differently the end effector, which is indeed more relevant, and to which we have assigned a given task velocity. And in this case, we add the repulsive velocity directly to the original task velocity. So we modify the task. Of course, as soon as there's no repulsion for the end effector recovers the original velocity. On the other hand, for the other control points, for instance, 8 control points here in this picture, and you can add no matter how many control points in this case, the repulsive vector will be considered as a Cartesian constraint. So you cannot go in a certain direction. Actually, you should go in the other direction. So it's like having an obstacle, a geometric obstacle that prevents you from going in certain direction. Now, this constraint is then mapped into a modification of the limits, the joint range and the joint velocity limits within the algorithm that we have seen already when dealing with redundancy, because here we are typically in a redundant situation. So using the SNS algorithm, the saturation in the null space, we have hard constraint at the joint level, and one of these hard constraints comes from the repulsive vector in the Cartesian space. Finally, before letting this guide the robot motion, we will saturate variation, so we will impose a jerk limited motion so that the robot will behave in a soft manner, and the human reaction to this, the human feeling when robot is moving more smoothly, is a sense of generic safety. For doing this, we have used sometimes the reflexes software, which modified the command so that impose also higher order limitation to differential quantities like jerk. So this is the overview. Let's look the operation. And this was in fact one of the first video performing this type of coexistence in a safe manner. So the robot is doing some task. For instance, it's doing the classical hexagon that we have used over and over to represent some generic operation. And now the human interfere with the original task. So the robot escapes at the end effector level now. And of course, not only for human parts, but whatever obstacle is being sensed. You can see below the depth image and the computation of the distances and of the reaction. And here is a classical pivoting operation when you have multiple obstacles and the robot escapes by pivoting around the center. And now you're considering the whole body. In fact, you can see that there are several control points in the depth image. And so you can avoid collision in this way. Indeed, if a collision occurs, the residual that you have built for this robot, so the signal that you generate in real time while moving the robot itself, will jump out of zero, detecting a collision and detecting possibly also which link collided, and either stopping the robot or reacting to the collision by abandoning the zone of contact as soon as possible, like in the floating or in the reaction, in the reflex reaction that we have seen before. This is the same experiment repeated in our lab and then developed over the years. Here there's a parallel simulation in MATLAB while the robot is running. So you can see the actual operation of the robot and the avoidance. You have also the video showing the depth image and the computation of distance and repulsive vector. But on the MATLAB 3D plots on the left-hand side, you see a skeleton representing the robot. And also you see how the robot is executing his task, is abandoning his task, again, an hexagon in the Cartesian space, and then resuming it as soon as possible. So you see that large avoidance, and now the end effector is going back to the hexagon. And now multiple obstacle, escaping, abandoning the hexagon, but then resuming it, and so on. Okay, so the main difference is this, and below you see the computation of the minimum distances from any object to the various control points on the robot. Okay, all this was obtained using a single Kinect. Indeed, there are some limitations. So the idea is you can put more sensor, in particular, more Kinects. Now Kinect is, I mean, even the version 2 is out of the market, but there are alternative similar system. At that time, a Kinect cost less than 100 euros, so it was a very cheap sensor. So you can equip the workspace with more than a Kinect, in particular with two Kinects, in order to solve the classical problem. The first problem is that there could be false collision, because if you're obscuring the view of the Kinect of the robot, of course, this is considered as a close obstacle, so its depth is associated to the depth of the control point. So it's like that this obstacle is very close to the robot, while in fact it is still far away. If you mount a second camera, and of course you have to calibrate the two systems, one with respect to each other, then you can recognize that this situation is no longer true. So this is the first things that you can, problem that you solve. You see that Fabrizio is putting a hand in front of the red Kinect, and the robot is avoiding something, although it is far away, while with two cameras, the robot continues to do exactly what it was doing. And of course, you can do other things with other objects as well. Now, the second problem that is being solved is the fact that beyond the robot, this is a gray area. So if you're approaching with the hand the robot from the back, this is not being seen, and in fact, you can touch the robot and the robot will not escape. On the other hand, with the second camera, you can detect objects that are also beyond this the robot, as seen from the first Kinect. There could remain some minimum gray areas, but we found that two Kinects were more than enough in order to solve these two problems. Now, the point is, if you have two Kinects, you have two depth spaces. So you're tempted to bring back the computation in the Cartesian space, because in the Cartesian space, of course, you can reason about vicinity very easily. But then you would give up the very fast performance of the Kinect. As you have seen in the previous video, the algorithm was running around 250 to 300 hertz rate. So we wanted to keep this fast computation. So in order to do this, we still work in the depth space of each camera. We have a leading camera, a leading depth sensor, and once we recognize this situation, we look at special points, special pixel, and the depth of special pixel in the second camera. So we need to make a calibration and association of pixel in advance when we place the two Kinect, but this can be done offline. So online, the computation is eliminated, in fact, so that we can run as fast as with one device. Now, just a comment on this fastness. You may know that these cameras provide 30 frames per second, so 30 hertz. So how can we run at 300 hertz instead if we don't have a new image? Every 10 image, or better say, for 10 sample, we keep the same image. So why we are repeating this and why we are claiming that we go faster than the frame rate of the camera? The reason is that there are two things in operation here. There are moving obstacles, humans, and we can detect where they are only with a frequency of 30 hertz. But the robot is also moving, and the distance is the distance between human and the moving robot. And we know where the robot is, in fact, at 1 kilohertz, because the fast research interface of the KUKA lightweight provides encoder data every millisecond. So this information updates the position of the control points, so we can recompute the distances with the frozen image for 10 sample. When the new image comes with a 30 hertz frame rate, then we will have the correct value. Otherwise, we have kind of a prediction. So we use this in the possibility of having two or multiple rates between the control of the robot and the speed of the sensor to get the best of both worlds. And we are running at this rate as shown. So this is not magic, it's just because we have something that runs faster than that, namely the data coming from the robot position. Okay, now I would like now to present some latest results of this human-robot coexistence that we have implemented in a recent project which ended in 2018. It's an H2020 program of the European Community. And it's a project of the Factory of the Future, so more application-oriented, where we try to bring into practice this idea of distance computation and coexistence. This is a cell that has been built by within the SYMPLEXITY project, in particular by a company in Modena, and with great operation of the University of Modena and Reggio Emilia, and with our algorithm for what matters the distance. Inside this cell, there is a huge industrial robot, an ABB IRB 4600, which has also the safe move option integrated. All the cell is supervised by PLC, and the communication have also a safety channel. And in fact, they use a protocol which is called Prof. So with Prof. Now, the task of this cell is doing abrasive finishing or polishing by fluid jets of metallic surface. Now, these operations are very dangerous for a human. So because of the technological process, there's no possibility of doing collaboration. There's no sense at all. But even coexistence, you don't enter the cell during this phase, but there are other phases which are still relevant, and you would like the robot to operate while the human is present. So the human may enter the cell to look at the part being manufactured or being polished, to look at the quality of this part, while the robot is holding another device, which is a laser device used for measuring the roughness of the surface, so to evaluating the quality of the operation. So in this case, we can implement coexistence, human-robot coexistence. So there's no contact at all. The robot is too large, too heavy, too massive for interacting physically with it, but we can be very close to the robot for looking at the object that is being measured. So during the measuring phase, or we can do visual check. And there are other possibility of contactless collaboration. We implemented a gesture-based communication, a very simple one, I would say. Now, in order to do this, we mounted two external Kinects to recognize the human gesture from the human, which is still outside the cell. And at the beginning, only two internal Kinects mounted at the corner, at the top corner of the cabin, as shown in the picture. And with this, we monitor distances. However, this sensor and the whole algorithm are not certified in the sense of safety. So this cell could be a prototype cell, but could not be really used in a practical application. So this is why we were asked to include some certified sensor, in particular laser scanner, for monitoring in parallel to the Kinects the environment. And here you see how we placed two laser scanners. This is the model, the Kinects model. They are placed at 50 centimeters from the floor at the two corners, and you see on the image on the right the coverage that they have at this height, so a 50 centimeter of height of the free part of the cell. Now, if the human is inside the cell, it's being tracked at 50 centimeter of height by this laser scanner. So indeed, this is not solving the problem. The Kinect are monitoring distance in 3D, while this laser scanner work only on a plane. So I could be with my legs at a certain distance from the table, which is the missing part in this in the left image. You can see the table in the 3D representation here. On the table, there is the part being manufactured or surface finished. So you could be far from the table with your legs, but in fact inclined with your trunk and your arms extended so that you're very close to the table where the robot is moving its device. So you see that you should be very conservative when using the scanners, while the Kinect, as we have seen, can measure distance very accurately in 3D and let you get closer in a reliable way. So the idea to solve this problem was a cascaded solution. I was skipping now the technical details. If you're interested, I can provide some reference to that. So because the cascaded solution, so having the Kinect in operation, monitoring their correct functioning, and when something was going wrong, for instance, the image remains stuck for a while, meaning that there's a communication problem, or there's a lightning that obscured the Kinect, and so everything becomes very dark or very light, all this situation, then the parallel working laser come into play, and the decision of slowing down or stopping the robot relies on this certified sensor. Okay. On the other hand, keeping the Kinects in place gives a more flexible sharing of the workspace between the human and the robot. So here, there are other things that should be done. Here you see the picture of the ABB is carrying an object, which is this kind of box, which is the CVS laser measuring device developed by a Swedish partner. So CWS stands for coherent wave scattering. So it's a measuring method using laser which are able to detect nanometer differences in the rugosity of the surface. So you have a CAD model of the robot that you use to eliminate the robot from the depth image, but the robot has now is equipped with other object. It has cables bringing power and pressure to the tool, whatever it is. So you have to use all this information in order to have a modified CAD model that you use for subtraction in the depth space. And this is represented in the image that you see here. So this is just to highlight that there are a number of practical problems. You don't have a naked robot like in the lab. You have other equipment that you should consider. By the way, on the table you see a part, which is a metallic part provided by Romagnani Stampi, an Italian company that produces metallic parts that are used for printing parts of the car bodies, plastic part of the car bodies. So they should be very accurate and very smooth and cleaned. Okay, and this is the overall control and communication architecture that we implemented. Around the ABB robot, we have the two Kinect overlooking the 3D space. We have the two-ladder scanner scanning at a certain level the free space inside the cell. There's a host PC that does the computation of from the Kinect data and receiving the joint position of the robot. All the communication are through the Profi protocol and eventually goes to the robot controller, which runs also the safe move. So we have an additional part of safety which limits the velocity of the robot as following the commands by the host PC. There are other switches, for instance, on the door state, and everything communicates. I mean, the orchestration of all events is done by a safety PLC. And you see that if the Kinects are okay, so the information is okay, and you're getting too closer, then you slow down the robot. In fact, if the Kinects are not working properly and the laser scanner are telling that the human is not far away from the robot itself, then you stop the robot. So you have a green light and a red light for doing this. And here I have a video. This is Andrea Carlesimo, one master's student who made the thesis within this project. So he's showing what happens when the robot is moving at maximum speed of 10 centimeters per second. It's a very massive one. And you can see how it goes inside the cell and what happens to the two Kinect images monitoring the cell on the right hand side. In this case, the Kinects are okay, except when one of the two is being obstructed on purpose to show that the second one can recover information anyway. You don't see the noise, but you see that Andrea is putting a hand in the vicinity. Now the robot stops completely. And you see that you can move relatively fast. And so the idea is not that the robot is doing its operation, is drilling or doing something which is very dangerous, but it's carrying the CWS measuring device. Now you have seen that he obscured one of the camera. So he's moving the measuring device. So now we have really coexistence, no? And it's looking or mimicking the fact that an operator is looking at the part to see if it's like it is expected to be. Probably also touching the part with his hand to feel the surface rugosity. Okay, now let's move. This was for coexistence. I could stop now, but I will continue a few minutes so that we can have a stop in a few slides from now. So let's move to the third layer of our architecture, collaboration. And in fact, we have mentioned that collaboration may be contactless or with contact, so physical. And I will present now in this short final part, the contactless part. So in contactless, it means that there's no physical interaction, but the robot and the human are exchanging information in different way. direct communication, namely I'm commanding a robot moves or don't move or making a gesture, or more indirect in the sense that I'm looking somewhere and the robot is understanding that if I look somewhere, the robot should do something. Okay, so following the eye gaze or the attention, giving attention to the human motion to recognize the action to be done by the robot. More in general, you can have a visual coordination so that you use vision in order to move at the same time in a coordinate way, not necessarily in the same way, but certainly coordinated between the human and the robot. On the other hand, physical collaboration, there's a contact. And if there's a contact, there's a force involved. And in order to understand what to do, the first thing that we will do is to estimate these contact forces, even without having a local sensor that provides this information. So we will see that we need some form of virtual sensing device. And once you have this contact force, you can use it for any purpose. So you can control the exchange of forces, but also the motion of the contact. So you can apply all the methodology that we have seen for controlling robots interacting with the environment. The only difference is that the environment now is a very dynamic one, is a human, is neither soft nor infinitely stiff, is unpredictable, and the geometry is very variable. So we have to adapt to this situation in a very reactive way. Okay, so this as a premise. Now let's say a few words and give some simple example of contactless collaboration. So first of all, you can use your hands, your head, your whole body, so different body parts to make gestures. The Kinect itself is able to recognize hand waving, which is the most simple operation. This is already, let's say, inside the software of the Kinect, together with the creation of a skeleton or human body, so that you can follow, since the Kinect was used for video games, it can reconstruct the skeleton of up to 4 or 5 person in the version 2 of the Kinect. So together with this recognition, it comes also the recognition of some simple gesture by hands. But indeed, you can set up a vocabulary of gesture, and it is important to recognize this in order to the robot to make the associated operation. Or you can give a voice command. There are very freeware speech recognizer. So you recognize voice command, and then the robot will start the collaboration and do something without contact, but collaborating with the human. In fact, you can do both things together. You can show the robot something, so do a gesture, while commanding something. So this mixed operation is very interesting. And here is an old video. It's one of the first videos which we had, where we were using Kinect and the SDK library, which is used for voice recognition. So the combination, the robot will move accordingly to the command, the voice command of the human, and the gesture that the human is doing. Here again, there will be some audio in this video, so I have to switch operation.
Luca, listen to me. Give me. Thank you. Almost nearest hand. Thank you. Luca, stop collaboration.
Okay, so you have seen this type of following, motion following. With different command, the robot goes to where Emanuele here had put the hand, so this is a go-to, or just follow the right hand, the left hand. You just seen just a selection of commands. The most interesting one is follows the nearest hand, the nearest as seen by the Kinect. Here in the video, you see two pictures. One is on the side to show operation, while the picture on the bottom part is the view of the Kinect, which was overlooking from the back of the robot the scene. So we mounted this L-shaped end effector in order to show better the orientation of the end effector. It is controlled in position only, so there is some redundancy, in fact, for this. And following means that the nearest end is the nearest hand to the Kinect. So if you, during the video, you have seen that Emanuele has exchanged his hand, so the robot had a change of direction and then started to follow the nearest hand to the Kinect. Okay, not the nearest hand to the robot. So this was for clarification. On the other hand, this is another situation, is in fact in the SYMPLEXITY cell. As I mentioned, we mounted also two external Kinect 2.0 here in order to recognize some gesture. And here you will see another master student of ours, Beatrice Procoli, who starts some gesture. And you see here the code that is she implemented, but in fact could be done other things. Opening or closing one or two hands, there's a first initial phase of activation, and then there's a final gesture also to deactivate. Now, while you will see the person with this motion, you will see on the in-picture window a skeleton of the human, and you will see a red or green ball around the hands when the Kinect has recognized the gesture, and this is then giving a command to the robot which is moving inside the cell. So the gesture have been activated now, and now you see both hands are closed or open, and the robot starts motion or stop motion or limit the speed. Again, one open, one closed. The limit speed has been taken out, and the robot has restarted moving. It's a very short video, but just to have an idea what can be done from the outside to the inside robot. Another possibility of communication and of programming, if you wish, or modify online the programming of the robot. Now, I mentioned that visual coordination is another possibility of collaboration, contactless collaboration. Here we have developed in our lab two types of possible visual coordination. So the idea is either you have a camera mounted on the end effector, so an eye and hand, which follows a human, for instance, the human head or face, so it keeps it always inside the line of sight, or vice versa, you have a human which has a camera or a Kinect on his head, on his helmet, or as we are doing right now, is using an Oculus, and from there it provides a relative information with respect to the end effector of the robot, which follows the human head. Okay, so the robot, there's a relative pointing and relative positioning at the same time. Now, in order to relax the pointing task, which requires 2 degrees of freedom, while the relative position requires 3 degrees of freedom, we introduced a cone. You can see it in these images. So that the requirement is that the pointing is either on the surface of the cone, and this is a one-dimensional task, or inside the cone, and this becomes an inequality, which when not active is not, it's like not having a task. When it's active, it becomes like before, so you're on the border of the cone, okay? So, in fact, this is very important in order to evaluate how many extra degrees of freedom you have. In our case, the robot is a KUKA lightweight with 7 joints. And if you were only interested in position or relative position, so following a path or being at a certain position with respect to the human head, this would involve 3 degrees of freedom. So you have a degree of redundancy equal to 4. If you had specified, like in the original version, position and pointing, you have 2 more task variable needed for the pointing part, so you go up to 5. So you had only a 2-dimensional null space available for any other reconfiguration. Indeed, if you're specifying position and orientation in full, you would have a 6-dimensional task. But in fact, we ended up with position and a relative angle with respect to the direction of pointing. So this is a relaxation, and we have, in this case, a task. This visual coordination task has dimension 4, so we have 3 degrees of freedom to be used for exploiting redundancy and, for instance, collision avoidance. Now, this is first a simulation. We use task augmentation method. Here, the camera should trace a circle. So the camera is tracing a circle, and the pointing direction of the robot with respect to the camera, it remains constant, and it should move at a certain distance from the camera. So this is the 4-dimensional task. Here you see the motion of the desired position and also the desired orientation, which remain constant. And the position error in this simulation using our controller was less than 1.5 millimeter, while the pointing error in radians is 6 to the 10 to the minus 3. So you see here now somebody is moving the camera, and the robot is following at a certain distance, pointing at the camera, or approximately pointing at the camera within a small cone. Of course, if the camera is now pointing upwards, the robot goes out of workspace. In fact, we built a sphere around the robot which defines the task limits, and when the task cannot be achieved, it's being achieved in a least square sense until it can be recovered completely. Okay, so this is to give an idea, and the actual implementation is in this following video taken in our lab. Here you can see the parallel simulation in VREP. Here, Khaled, one of our PhD students, was holding the Kinect and moving it around. We specified a certain distance, and the whole task is being reproduced in VREP on the right-hand side. You see the blue sphere, which defines the task limit. In fact, the camera is out of the workspace, but the robot is following a projection of the camera on the surface of the sphere. In this first version, we needed to localize the camera with respect to the robot, so the Kinect with respect to the robot, and we use this marker placed on the table. When we move to the following situation, which is the one depicted here, so with the Oculus Rift here mounted on a helmet and then mounted completely with augmented reality also included, then we didn't need this localization. We used the localization of the Oculus Rift itself. Okay, so let's stop this first part here and resume the second part on physical collaboration next. Thank you for listening.